well, this chapter is actually roughly half of it is like a revision of what you've done in the IG level. But it's a revision of that, but it also extends this knowledge to more details that we are going to discuss in a few lessons. So here I have roughly all these items here are roughly what this chapter is all about. The top items here represent the chemical bonding that we find between atoms, and the three types of this bonding that we met in the IG level, which is the ionic bonding, covalent, and metallic bonding. Those three types of bonding, which these types of bonding, it's actually, let us distinguish from the bottom part of what I have in my notes here, is this type of bonding exists between atoms of elements. These very strong bonds, whenever atoms appear in clusters with very strongly bonded between one another, we call it chemical bond, and it could be the ionic or covalent or metallic. What is this? Metallic bonding. Sorry, metallic bonding. Now, these bonds exist within a molecule or between atoms. And but now the following items here, which we meet in between molecules, molecules in a solid material especially, but also in liquids, also bond between one another, not with strong forces like the forces we find within a molecule, but nevertheless they do bond. I mean, molecules in a solid or liquid exert forces between one another, and these forces is what we call intermolecular forces, intermolecular forces. Which we say are weaker than the bonds, but nevertheless they are there and they keep a solid or a liquid together. And again, these forces come in different variations. We have three here, a list of three. The van der Waals forces, which the van der Waals forces actually is it's a cluster of many different types of forces, relatively weak forces between molecules, and sometimes they are called dispersion forces, or and when we are going to talk about these forces, we are going to see that they are the forces that exist between dipole, induced dipole, and so on. They come in different variations. Now, don't worry about that for now. But nevertheless, all these forces are called van der Waals forces, and there are also other intermolecular forces which are stronger than this, which could be dipole forces, and another type, a third type of intermolecular forces, which are actually the hydrogen bonds. And we're going to discuss each and every one of these. But for now, in this lesson and the next, we are going to concentrate to focus on the chemical bonding. And in this lesson, since it's the first lesson and the introduction to this chapter, maybe we can discuss this as the chapter in your book begins in any case, by looking at the different types of bonding generally, and to remind us what we have met in the past. And your book starts from the ionic bonding, from these types of bonds. The ionic bonding, which I don't know how much you remember, but let's discuss it quickly. These are usually bonds between metals and non-metals. And if we look in the periodic table, let me find the periodic table. You know, remember that most of the elements in the periodic table are metals in any case, except only these are the non-metals. Anyway, the bond between a metal from this part of the periodic table between a metal and a non-metal is an ionic bond. It's an ionic bond. There is a reason for that. There is a reason why this is an ionic bond and not a covalent bond. But we are going to discuss as we see some examples. So remember, the ionic bond is between metals and between a metal and a non-metal. Forms an ionic bond. And remember also, apart from atoms of elements, we also have these clusters of ions that are made of many atoms. And we need also to bear this in mind. But nevertheless, now let's go back to our notes. So the ionic bonding is a bond between a metal and a non-metal. It involves a transfer of electrons, not the sharing of electrons, but a transfer of electrons. So electrons from the metal transfer to the non-metal. And the result is the formation of ions, positive and negative ions. Positive ions and negative ions. And the reason why the two items, usually atoms, that are involved in this type of bonding, they are attracted to one another because of them being ions, because positive and negative particles attract one another. As we learn in electrostatics, unlike charges attract one another, they follow this rule. So because we have ions, ions are charged particles, a positively charged particle and a negative charged particle attract one another with a very strong electrostatic force. And this is the attraction that is involved in this ionic bonding. So the ionic bonding, it's actually an attraction between positive and negative charged particles. So let us see now this first example, which is the easiest example, and all the books start with this example, which is the sodium chloride. Here we have an atom of sodium, a neutral atom of sodium, which sodium has 11 electrons altogether, of which only one is in the outer energy level. It has one valence electron, in other words. Here it is, this one. And a chlorine atom, there is a chlorine neutral atom, has 7 outer electrons in this outer energy shell. So you see, for the sodium atom, it's easier to give away this extra electron, this single electron in its outer energy shell, than pick up another 7, isn't it? It's easier to give this electron than take from someone else, some other atom 7. So, and the same applies to all metals. That is why metals usually give their electrons, and non-metals like the chlorine represents the non-metal with 7 electrons in its outer shell. It's easier for it to pick up one extra electron to make it 8 to acquire the noble gas configuration, which is usually represented by 8 electrons. Well, roughly this rule. So what happens here? So this sodium can give its electron to a chlorine. Here, this electron moves to the chlorine, and now chlorine has its 8 electrons altogether in the outer energy shell I'm talking about. And sodium is left with a complete this second energy level now is what is left, which is complete. And both of them now are happy because they both have the electronic configuration of a noble gas. The sodium has the electronic configuration of neon now. If it gives it its electron, it will remain with a configuration of neon, which has 10 electrons in it altogether, or 8 electrons in its outermost energy level. And chlorine also acquires an outer energy shell with 8 electrons, which is actually the electronic configuration of argon. All right. So now you see, this is what remains from the initial neutral atom of sodium. We have this remaining now. It is left with only 10 electrons, But remember, the sodium still has 11 electrons in its nucleus. Not electrons, protons, 11 protons in its nucleus, which means now altogether, this is not a neutral item anymore, neutral species. It has an extra proton here in the nucleus, and therefore it has a charge. Now this is a charged particle now, and we call it an ion, positive ion, or cation sometimes, cation. Cation, when you hear the word cation, means it's a positive ion. It's the same thing, positive ion. Now the chlorine, now the initial chlorine atom picked up this electron, and now it has how many is 18 electrons altogether it has now, isn't it? Because chlorine by itself, chlorine has 17 protons and 17 electrons, a neutral atom. So now this chlorine here has 18 electrons. It has 18 electrons altogether. But in the nucleus, it only has 17 protons, which means it has an extra electron, which means altogether now, it's also an ion. It's a negatively charged ion, and or an ion. And an ion is a negative ion, same thing. So both of them are ions now. The one is a positive ion, the other one is a negative ion, and they attract one another with via the electrostatic force. They follow the rule, unlike charges attract. So the moral of the story is that the ionic bond relies on the attraction, this electrostatic attraction between a positive and a negatively charged particle. So this is the moral of the story for the ionic bonding. And of course, we can see more examples. We can see how to represent these items, like in your book on page, page 50. On page 50, actually, let's do it. They suggest a way to represent this transfer of electrons. But there is a lot to be said about that. Let us start systematically now with sodium chloride again. I mean, it's not a matter of being the same. It's a matter of how to go systematically to find what is going on with the outer electrons. So practice drawing diagrams of ionic bonding. Diagrams of ionic bonding. What are these diagrams of ionic bonding? It's something like this. This will be the final result. And how do we get there? When we show an example of how to represent the cation, which is the one that gives one or more electrons, and the anion, which is the one that picks up electrons. In order for us to distinguish what is happening, there is a suggestion to use, to represent electrons in one of the species with a cross, like an X, like here, and in the other species with a dot, simply just to distinguish which electrons belongs to what and where do they come from. And also another thing, when we draw a diagram for this type of bonding, when we need to show which electrons have been transferred, we don't need to draw all the electrons of the two atoms. We just draw the electrons which belong to the outer energy shell, like here. So sodium has only one electron in its outer shell, whereas chlorine has only 7 electrons in the outer shell. But they have more electrons, of course, in here. I mean, they have other energy shells, but we are not interested in the core energy levels, because in the core electrons, because it is only the outer electrons. Well, this is what we believe, that are involved in any chemical processes and in the sharing of electrons and in the bonding and and the giving and so on, transferring of electrons and bonding in general. It's always the outer electrons, or valence electrons, as we call them, that are involved. So we don't have to draw all the other electrons in the inner energy levels. Not that it would be a mistake or wrong to do it, but I mean, there is no need. Now, I mean, how do we know now how many electrons are there in the outer energy level? Of course, one way is to find out how many electrons, how the electrons are distributed in the energy levels, or we can simply write down this this electronic configuration of each atom, if we can do it, if we remember how to do it, the electronic configuration, or simply we can go to the periodic table and see in which group these items are. We have a sodium here, for example, and a chlorine. In which group is in the periodic table is sodium? It's in the first group, group 1, and chlorine is in the group 17, or the previous, or the main group 7, which is symbolized like that. So if an element is part of a group 1, obviously it has one valence electron, one electron in its outer energy shell. So we know that sodium will have one electron just by by finding which group it belongs to. Chlorine, belonging to group 7 or 17, has 7 outer electrons. So it's actually very straightforward to go to the periodic table if we don't remember and find out where are they, where do they belong. Well, of course, this is easier said and done if we talk about elements which we find in the main groups, because elements which are found in the transition, which are part of the transition metals, are not so easy either, because they can have different valences. But nevertheless, the problems that we are going to see in most cases will be dealing with elements that we find in the main groups. So it's easy to find out how many electrons they have in the outer energy level, so we can draw them. So you see sodium here, they chose to have the X to represent its single electron, and chlorine, they chose to have a dot there representing its outer electrons. So when the two join, when this electron is given to the chlorine, we can put an X there, and this one disappears. And what do we have? We have the sodium ion now left behind, which we can, oops, this one plus missing. We can represent it like that as a positive ion. And here we have a chlorine, the chlorine with its 8 now electrons, 2, 4, 6, 7, and the one will be with an X because this X now comes from the sodium. And this will be now a negative ion with a charge of -1. And this is how we can represent this. This is a diagram of ion bonding corresponding to sodium chloride. What else? In your book, I must say, this AS book, they suggest that you show here an empty energy level around the sodium, just to show that it has this electron has left this energy level and it's empty now. This is not really necessary, and it's not a very wise idea. Let me show you how it looks in your book. I have it somewhere. Yeah, there it is. This is how they represent it here, this one, this diagram. It's from page 50 in your book. They show this empty energy level to show that it has no electrons anymore. And this is the X, this electron that came from the sodium, originates in the sodium. And this is how they represent it. But I must tell you that this is not a rule on how to represent this diagram, the two ions. There's no particular rule of how to represent it. So this author of this book, actually there are two authors, they chose to represent it this way. In the previous book, in the IG book, they show it in this representation. This diagram corresponds to your IG book. This is from the AS book, this is from the IG book. So you see different authors represent it differently. And if you go on the internet, you're going to see millions of other representations, as long as it makes sense. Frankly, this representation, to tell the truth, I don't find it very wise at all. Because when a cation forms, when a metal gives it 1 or 2 electrons to something else and forms an ionic bonding with something else, because its outer energy level is empty now, it's like we don't need this anymore. What remains, the sodium ion that remains, is actually a lot smaller than the neutral atom of sodium. So if the neutral atom had a size like that, the ion now has a much smaller size. That will be the positive, that will be the neutral. Similarly, for the anion, the formation of the anion picks up one electron or more, depending on with what it bonds. And actually, now this anion, the negative ion, has a much bigger size than the neutral atom before the bonding. So for the anion, if the neutral atom, say, has this size, the anion has a much bigger size. That will be the ion, and this will be the neutral. You might say, why does this become bigger, since it's still the same outer energy level? It has not added extra energy levels. No, but because it picked up one electron or more, and because the electrons now repel one another, it blows up a bit and becomes much bigger. So that is why I don't really like this idea of having here an empty energy level, because we might forget that this now becomes a lot smaller than its neutral configuration, the neutral atom. Anyway, it's not like a big deal, but the moral of the story is that be careful. There's no rule of how to represent this exactly where all chemists agree. For example, you see this one and this one are a little bit different configurations, but they're both correct and they both make sense, okay? All right, let's stop sharing. Good morning. People, do this make sense, what I'm saying here? This links to the periodicity in ionic radii in chapter 10. Yeah, of course. That is why I wanted to say that, because we are going to need the ionic radii later on. Absolutely. Yeah. All right, let's share again. Okay. I don't know if you wanted to do some examples here. Let's do magnesium oxide and then let's go to the covalent bond, because, oh, 1154, oh dear. Magnesium oxide. Let's see the magnesium oxide. How are we going to represent this ionic bond? First of all, you see this is a metal and this is a non-metal. Obviously, this is an ionic bond between the two. Magnesium. Where is the magnesium? The magnesium is part of group 2. It's a group 2 element, and it has 12 electrons. It has an atomic number 12, and the oxygen is part of group 16, or the main group 6, old numbering. And the oxygen, of course, has 8 electrons altogether, or 8 protons. Okay, so magnesium and oxide, how are we going to represent their bond? You see, since this is a group 2 element, we know that it has 2 outer electrons, 2 electrons in its outer energy level, 2 valence electrons, whereas the oxygen, being in a group 6, has 6 electrons in its outer energy level. So we can only draw the outer energy levels, one for magnesium, say this magnesium, and this is the oxygen. Magnesium with its 2, let's make them crosses. 2 crosses to represent its 2 outer electrons. The oxygen has 6. 1, 2, 3, 4, 5, 6. Now, the magnesium can give away its 2 electrons. The oxygen can pick them up because it needs 2. So this and this can go there, and we'll have, how can we represent this now? We'll have the magnesium without any outer energy level, which, and it will have now 2 missing electrons, which will leave it a positive ion, a cation with a 2 plus charge. And the oxygen with its 2, 4, 6, 8 outer electrons now, but and the charge of 2 minus. So this is how we could represent this. Magnesium fluoride. Let's write it. Magnesium is the same thing. It's the same element as before, with its 2 outer electrons. with the magnesium. Now the fluoride, though, the fluoride ion, fluorine atom, a fluorine atom is part of the halogens. It has 7 outer electrons, which means it has space only for 1 electron. 2, 6, 8, 7. You see, each fluorine atom has space only for 1 electron, which means the magnesium can give 1 of its electrons there, but then it needs another fluorine atom. So we need another fluorine atom. We need 2 of these. 2, 4, 6, 7. So the other electron from the magnesium will go to the other atom. So we have, overall, we have the magnesium at the end that will have a charge 2+, and the two fluorine atoms with a charge of -1 each. 2, 2, 2, and like that. So we have the coefficient 2 in front of the fluorine ion because we need 2 of these to join with the magnesium. By the way, one last thing before we stop. I'm panicking with this thing because it's 11:58. One thing before we stop is this. We say now the magnesium gives and this one takes, which is kind of a silly expression. It's not like we personalize the atoms. What happens really is that, you see, the non-metallic elements, the non-metals like oxygen, chlorine, and so on, are very electronegative in comparison with the metals, and especially the metals of the first 2 groups. Yeah? So because their electronegativity is a lot bigger, what happens is they attract they attract electrons from the metal atoms, and this is how they kind of end up with the electrons all to themselves, and they leave the metals with missing outer electrons, their valence electrons. So it's a matter of electronegativity, really, this ionic bonding. It's these electronegative atoms attract very strongly electrons, and this is how this bond ends up in the formation of ions, and then the ions, positive and negative ions, attract one another. And I think that is enough with ionic bonding. Okay, next week, I think we're going to do covalent bonding and do it as fast as possible. And especially, I want us especially to pay attention to the difference between the covalent and ionic bonding and how to recognize it, because sometimes it's easy to be fooled between the two. All right. So it's a redox reaction with oxygen. Let me read properly. It's a redox reaction with oxygen being the oxidizing agent and magnesium being the reducing agent. You have moved a lot, I see. Yeah, right. That is very true, very, very true. So next week we continue with this bonding. And guys, if you have any questions on this type in this chapter, please bring them here so we can discuss it. Because if you are by yourself, you're already quite a lot ahead, maybe you need some more substantial stuff in the bonding. All right.